Hi, hello, namaskara. In today's session, we are going through the small derivation, that is relation between the J, sigma and E. We are taking here J, sigma and E. From the last session, I think we gone through what you mean by the J here, where J defines the current density and it's a vector quantity we have seen. And if I write the equation for it, that J is equal to I divided by A. Current per unit area will give us a current density, and its SI unit is what now here? Ampere per meter square. We have seen that now, right? Thereafter, as per today's derivation, we have to go through another concept. That one is a new symbol. I think you have seen in the beginning of the slide, that is sigma. Okay, what is the sigma here? Sigma defines the conductivity. Sigma defines the conductivity. It's exactly opposite to that of resistivity. Okay, we have seen what you mean by the resistivity rho in the last session. Therefore, conductivity is the reciprocal of resistivity. Therefore, we can define conductivity sigma is the reciprocal of resistivity. This is how you can write it. Therefore, sigma is equal to 1 by rho. I can express here now. Okay, now if I want to write the SI unit for that, now already we know that here, as per the idea of the resistivity, what is the SI unit for the resistivity? That is ohm meter, right? That will be what now? Ohm meter. If it is so, then I can get the answer for what is the resistivity for now conductivity. If I take the reciprocal of it, that is per ohm per meter is the SI, otherwise yeah, unit for what now here? It's a conductivity. Okay, there is another method, that is 1 by rho. 1 by rho can be written as with the another symbol, that is we are writing 1 by ohm as mho. 1 by ohm as 1 by ohm as what now here? Mho, MHO. This is how they are writing now. Okay, therefore the above SI unit will become now. The above SI unit will become now like this one now. That is, it's very simple. It is becoming now ohm, sorry, it's a mho meter now. It's a mho meter. That is, it's a mho per meter. That is the only difference we are having now. When I take the mho, that's the reciprocal of ohm. If I take it, that will be mho. Okay, mho per meter will be the SI unit for what now here? Conductivity. Okay, now after this one, I want to introduce another idea, that is about the electric field. About the electric field, I think you know that from the your basic classes, otherwise your classes in 8th or ninth. I think you know that what do you mean by the electric field. What do you mean by the electric field? For example, if I am having a charge, around that there is some electric field lines which are coming out of the charge now. Okay, therefore around this charge, what the diagram I have written here, that this diagram shows about what now here? Electric field. Therefore, how can we define the electric field? It is the space around the charge where we can experience the electric effects like attraction or repulsion. I'll repeat, it is the space around the charge where we can experience the electric effects like attraction or repulsion. For example, if I put the positive charge, what will say? It will repel. If I'm keeping a negative charge, it will attract. Means what you are telling, that if there is no field, then there is no interaction we are observing. As there is a field, therefore we are observing. That observation we are doing in some field, that field only is nothing but what now here? Electric field. Okay, now, with this information, I want to remember another equation from our 10th class, where we have written another idea. That one is V. I think you remember what is V here? V is a electric potential. V is what now? It's a electric potential. Therefore, what is electric potential? From your lower classes, you know that electric potential is work done in taking a charge from one point to another point we have written. Therefore, we are having the equation V is equal to W divided by Q. Now, how to understand this equation? Okay, in today's session, remember one thing, because I'm too many equations using from here and there, and this equation what I'm discussing now, this sheet what I'm discussing now, you are studying this about this one in a detail in your chapter 2. Okay, therefore don't bother about it. Now try to understand only what I'm explaining. That's enough for the my further sessions. Okay, now here I'm clearing again. Electric potential is what? Now work done in taking a charge from one point to another point. Okay, therefore W divided by Q, we are having this equation now. Okay, how to understand this one? Therefore I'll take one small idea here. If I'm having a positive charge, around that there is a electric field. Around that what now? There is a electric field. I'll take 2 3 points now. I'll name here point 1 and I'll take here point 2 now. Okay, now if I ask you, in what position you are experiencing higher potential. For example, first I'll take here positive charge one time at position 1 and position 2. Okay, if you observe, when I keep the charge at point 2, we are doing, remember, very less potential, otherwise we are experiencing less potential, because when I'm very far away from the charge, when I'm very far away from the charge, the effect of the electric field is very less. The effect of electric field is very less. Therefore work done will be less. Work done will be less. Therefore we can say here work done will be less. Therefore I'll take it for the comparison. I'll write it here what the work I'm doing to place the charge at point 2 as what now here? W2. Similarly, if I take the same charge and keep at this position, if I take the same charge and keep at this position, that is position 1, if you ask me what is the potential, otherwise what is the work done at this potential point, then I can say here work done will be how much now? It will be 1 now. If I compare both the things, work done at W1 and W2, you can answer me, remember, at the position 1 work done is more than the position 2. Therefore I can say W1 is greater than the W2. W1 is greater than the W2 because this point is near to the charge and this point is farther to the charge. Now whenever we are very near to the charge, the potential is more, work has to be done more, because a positive charge, it will be repelling. Therefore I have to, if I want to keep the charge here, I have to do the more work, then only I keep that charge. Therefore your work done will be more, your work done will be less. Okay, therefore all these ideas we are understanding in this one, and the difference of this work done we are calling it as what now here? Potential difference. I think you remember delta V is equal to W by Q. We can also write it now. By understanding all this concept now, that is J from the last class and electric field in today's class, we are writing a new equation today. That is, we are finding the another equation for the Ohm's law, but it's a microscopic form of Ohm's law. That will be, we are deriving the equation J is equal to sigma E. But to derive that, I need another equation. I need another equation, that is relation between the electric field, relation between the electric field E and electric potential V. I'll give the small glance on that. I'll take that equation and we will derive this equation. Therefore, have the patience. Therefore, I'm telling, I am taking many equations from the last chapter also. Okay, therefore, have the patience now. Okay, that is, now what we are doing here, let us say, here we are having a charge now. Okay, around that there is a electric field now. Around that there is a electric field now. Okay, now I am writing here E be the electric field. E be the electric field now. Okay, now And if I'm taking 2 points, let us say at position 1, I take it as a potential V1. Similarly, at another position, I take it as point 2. That position, at that position, the potential will be how much now? V2. Now, I think you can able me to answer the equation what I am writing, because that equation will tells us what the explanation I had given in the last session. Let us check it, that equation now. I am writing the relation between the electric field and electric potential is given by E is equal to dV divided by dx. E is equal to dV divided by dx, where E is the electric field, V is the electric potential, and x is the distance at the point of interest. For example, point 1 and point 2 is the point of interest. From this equation, we can observe here E is inversely proportional to distance. E is inversely proportional to distance. That is, as I move away from the charge, the electric field goes on decreasing. I explained the same thing. At this position, if I take the potential of 5 unit, and at this position, the potential must be less than this 5 unit. It will be somewhere, let us say, 2 unit now. Therefore, as I move away from the charge, the electric field goes on decreasing. All this explanation I can bring in this equation. Therefore, we are writing here E is equal to dV by dx. Okay. Now, to make it simple, the above equation write in this way. E is equal to what I am writing here, dV divided by dx. Instead of that, I'll write it here. I'll remove that differential form. I'll remove this d and I'll write it on the equation with the original form, where E is equal to V by X, where V is the potential difference and X is the distance from the charge. Okay, by understanding this equation, now we are deriving the relation between the electric field, that is E, J, and the sigma. I think you already know what you mean by the sigma already. And J equation, you know that's J is equal to I divided by A. And I want to make you to remember another equation, that is R is equal to, that will be a rho into L divided by A. I'm using this equation also. Okay. Now we will derive that. Now what I will do, I'll consider a conductor now. I'll consider a conductor of length, how much it's of L now. I'll consider a conductor of length L, in which we are having a electric field of E. In that we are maintaining a electric field of V, so that there is a potential difference of V across the ends. If it is so, then I will take the equation, that is E is equal to V divided by X. E is equal to V divided by X. I already told you V is the potential difference and X is the distance. Now tell me, from the above diagram we can see we are applying this electric field for a length of L by maintaining a potential difference of how much here? V. Therefore, we have the all the terms in the diagram what we need for the equation. E, we have the V, but what is this one? Distance X. Okay, this electric field we are observing for the complete length. What is the length of that? Is it X or L? You can see in the diagram it is how much? L. Therefore, we have to write here V as it is and take this X out and write it as L now. Therefore, the equation turns out to be now E is equal to V by L. Otherwise, I can write here E into L is equal to V. Otherwise, more properly, I can write here potential difference V is equal to product of electric field and the length for which we are applying now. Take it as equation 1 now. Take it as equation now 1. Now, from Ohm's law, we know it now. What is Ohm's law equation? That is V is equal to IR. V is equal to I into R. Therefore, we can see I'll take it this equation as 2. Now compare the equation 1 and 2. We can have here on the LHS. On the LHS we are having the same term. Therefore equating 1 and 2. Equating equation 1 and equation 2. Let us see what the result we are obtaining now. Therefore we are writing here on equating E into L is equal to I into R now. E into L is equal to I into R. Now what is our aim? I had to bring the equation J is equal to sigma E. Out of this one we are having only what now? Electric field E only. Still we are missing the J and sigma. Therefore what I will do, I'll write here as it is E into L is equal to, instead of R we'll substitute a new thing. What is that now? Already we know that R is equal to rho into L by A. R is equal to rho into L by A. Already we know it now. Already we know that concept. Therefore what I'll write, instead of R I'll write it here rho into L whole divided by A now. On doing so we can cancel here L and L will be cancelled off. As a result we had now only E is equal to, that is I into rho divided by A, divided by A. Therefore, if you keenly observe this equation, we are having another term here, that is I divided by A. Already we know that. What is I divided by A from the last session and today's today's session I told you. What is I divided by? Current per unit area is nothing but what now here? J now, that is current density. Therefore, I can write, instead of I by A, I can write it here J into rho. Therefore, this is the equation we are having now. E is equal to J into rho is the equation. Still, we are missing with what now here? Sigma. We got now J, we got now E, but we are missing what now here? Sigma. We know that. We know that. What is that? We know that. That is rho can be written as 1 by sigma. Rho can be written as what now here? It's a 1 by sigma, and we know that reciprocal of a conductivity. Reciprocal of conductivity is resistivity from the beginning of the session. Therefore, what I will do here now, I'll bring this to the LHS side. Therefore, it will become now E into 1 by rho is equal to what now here? It's a J now. J. Now, here we know that 1 by rho can be written as what now here? It's a sigma. Therefore, I can write now E into sigma. I can write it here E into sigma is equal to J. Therefore, we can observe here, that is J is equal to sigma E. That is the required equation. I have got it here now. Clear? This one is called with another name, that is microscopic form of Ohm's law. And if they ask you this one in the exam, it will be merely for 3 marks. Okay, now I want to write the same thing in vectorial form. I want to write the same thing in the vector form. Therefore, J, already I told you, it's a vector quantity or scalar quantity. Current density is a vector quantity. Therefore, I'll write it here, J bar is equal to sigma into E, where sigma is brought from which idea? Resistivity. But resistivity basically is a scalar quantity. Therefore, if a resistivity is a scalar quantity, then automatically I can say sigma is also a scalar quantity. Therefore, I can't put the vector on it. Therefore, it will be termed as scalar. And electric field is having already direction from our explanation. Therefore, it must be a vector quantity. Therefore, I can say here J bar is equal to sigma into E bar is the vector form of microscopic form of Ohm's law. That is J is equal to sigma E is the vector form. Okay, understood. These are some ideas regarding what now? Derivation. Now if you want to have the clear picture, you can observe here from the diagram. You can write on your sheet for the practice, and already I think sir has provided in the group the notes of this complete chapter. If not, you can message me on my number. I'll give you that notes in PDF form. Okay, and for any doubt you can message me on this number, that is 82 174 7. I'll repeat, 82174 is the number. On this number you can send your doubts, otherwise you can ask for the notes. I will message you. Okay, now understood. This is the today's session. I think in today's next session we are getting into the another important derivation. That one is a drift velocity. Okay, for that try to go through some kinematic equation and the Newton's law, that is F is equal to ma and V is equal to u plus at, S is equal to ut plus half at square, V square is equal to u square plus 2as, and another equation V is equal to u plus at. Try to go through all these four equations. That will be helpful in next session. Okay, we'll wind up today's session here. Thank you.